Hello and welcome. Today we want to go through the complex numbers. It's the introductory part, but we have a main course which is called complex analysis. Today we want to introduce complex numbers. Now, a complex number is defined as a number C such that we have x plus iy, where x and y are real numbers and I squared is equals to -1. X is called the real part and y is called the imaginary part. We can also call the real part is also written as RE of Z. The imaginary part is written sometimes as IM of Z. And we define a complex number as Z is equals to x plus iy. We have said x is the real part, y is the imaginary part. That means you can say that Z is equals to RE of Z plus IM of Z. That is also another definition of a complex number. And just like real numbers, complex numbers, we have operations on complex numbers, and one such operation is the addition. And you know the way we handle addition is the same way we handle subtraction. So we have the addition property. Let's just write here operations on complex numbers. In real numbers we can add, subtract, divide, do all that the same as in complex numbers. We have addition. Say we have a plus ib. That's one complex number, and this complex number is being added to another complex number c plus id. Now what happens is you add the real parts together and then you also add the complex parts together. Now we will have a plus c plus I into B plus D. We have multiplication. We have a plus ib. That's our one complex number, and we have another complex number c plus id. Then we conduct the normal multiplication. We will have a into c plus id plus ib into c plus id. We open the brackets. We will have ac plus ad, but now that has the I, plus bc, we have an I, plus bd I squared. What did we say about I squared? We say I squared is equals to -1. We'll just say but I squared is equals to -1. That means that sign will change. We're going to get ac minus bd plus I into ad plus bc. And now that's how we conduct matrix multiplication in complex numbers. And now when it comes to division, we have the division of two complex numbers. We are going to use what we call complex rationalization. When we are dividing two numbers, we apply what we call complex rationalization. Complex rationalization. Say we have a plus ib. We are dividing c plus id. We will multiply. We will rationalize the denominator and then multiply it through. And now we will have a plus ib times c minus id over, this is a square, we will have a difference of two squares, so we'll have c squared minus d squared. And that's how we handle the operations on complex numbers. That is what happens. We will have a few examples you can be given to simplify. You are given a complex number and then you are asked to simplify. For instance, you are told 5i to the power 4. This is the same as 5i squared times I squared, which means you will have 5 into -1 times -1. That gives you a 5. And then assuming you are given 8i cubed, this is the same as 8 cubed I cubed. That gives you 512 I squared times I. We will have minus 512i, since I squared will give us -1. About division, let's handle one example so that you can see how we rationalize. We will have, first, when you're rationalizing, we will have z. Say you have z is equals to a plus ib. When you rationalize, you will have z bar, which means it will be a plus ib or bi bar, which gives you z minus the b of I. That's what we call rationalization. Now, for example, you're given two complex numbers, you're supposed to divide them. And remember that when we say division, this means that these complex numbers are just to power 1, meaning they're not to any power above 1, plus 4i. So we rationalize, we will have 3 minus 4i, 3 minus 4i. When we handle that, the denominator is a difference of two squares, so we will have 3 squared minus 16, which means in the denominator we will have 25. 9 plus 16 gives us 25. And then we will multiply 5 plus 2i by 3 minus 4i, and now that will give us 23 minus 14i. Our resulting complex number is 23 over 25 minus 14i over 25. That one we have written in the form z is equals to a plus ib. And now that's how we perform the operation of division and dividing two complex numbers. And just like in a real plane, we have the Cartesian plane or the coordinate plane. In complex numbers, we have something we call the Argand plane or the complex plane. The Argand plane was discovered by somebody who is called Argand. So we have the Argand plane. The same way you can represent the real numbers on a Cartesian plane is the same way you can represent the complex numbers on an Argand plane, also known as the complex plane. Another name is the complex plane. We have the x-axis. This one is the real, it has the real numbers, so we call it the x-axis or RE. But now the y-axis here, it has the imaginary numbers. Now here we will have I, 2i, 3i. Then here we have negative I, negative 2i, negative 3i. we have 1, 2, 3, 4. The real numbers are represented on the x-axis, while the real part is represented on the x-axis, while the complex part is represented on the imaginary axis. We have -1, -2, -3, -4. You can go up to as many as you want. Now we have two examples. We are given to represent z is equals to 3i on the argand plane. So we have 2 is the real part, and we have 3 is the imaginary part. Now we will come here. We have +2 and we have 3, and now at this point is where we have our point 2 plus 3i. Assuming I've been given another -2 minus I, you will have to go to -2. It's here. The real part is -2, the complex part is I, and now you indicate here -2 minus I. You can indicate anything you want. You can have something like 3i. We have 3 minus 3i. Now that's how we indicate, or we plot on the argand plane or the complex plane. It's similar to the coordinate plane. The only difference is that our y-axis is what contains the imaginary values. Another thing you can use, or you can get from a complex number, you can get the modulus, you can get the angle. The modulus, we have the modulus of z. We can get the modulus of z. We have z is equals to x plus iy. The modulus of z, we indicate it with sz between two straight lines, which is equal to x squared plus y squared. Assuming that we were given that z is equals to a plus bi, then our modulus for z will be a squared plus b squared. Let's now get a real example. You can be asked to find the modulus of z, and you're given that z is equals to 4 plus 3i. Then that means we will have the modulus of z will be equal to 4 squared plus 3 squared. That gives us the root of 25, and the root of 25 is 5. Another thing that you need to know in this introduction part, we have the polar form of a complex number. A complex number can be written in polar form. Polar form of a complex number. You're given, let's draw here. We have our axis. This is 0. We have y. We have the y-axis or the imaginary axis, and then we have the x-axis or the RE. This means it makes an angle here of theta degrees. That distance is r. Let's extend this here. And if it was to make on the other quarter also, we could have an angle here. The only difference, then our angle becomes -30. We have -30. So this distance here, let's call it xy, and now this distance from here to here, let's call it x. And now when this angle goes here to 90 degrees, we know the SOHCAHTOA. We have theta here, we have our y, we have our x, and this makes 90 degrees, meaning that x, and this is r. We have cos theta is adjacent over hypotenuse. If we want to make x the subject, then x will be equals to r cos theta. Our sin theta will be y over r. That means if we make y the subject, we will have r sin theta. R sin theta. And now if you want to write our complex number in the form of r, and we will have x, so we will have r cos theta plus I r sin theta. That means we have r into cos theta plus I sin theta. But now we have an identity that's called the Euler's identity. Euler's identity. And Euler's identity states that cos theta plus I sin theta is equals to E I theta. And now that means our Z is equals to R E I power theta. And now that's our polar form of that complex number that we have. But now theta will be found using tan inverse y over x. And you can always be asked to convert from Cartesian to polar form, or from polar form to Cartesian form. Either way, it works quite easily. When you want to get tan theta, still going to use this. Tan theta is opposite over hypotenuse, meaning you have x over y. So to get the angle, you get the inverse of tan. Let's see an example. You have been given that z, the modulus of z is 10, and you have been given that the angle, which is sometimes called the argument of z, is 120 degrees. And then your question asks you to find z. So you want to find z, or in other words, you write z in the normal rectangular form. Rectangular form is also the Cartesian form, it's the same name. So we have z, we are expecting z is equals to r into cos theta plus I sin theta. And you know the modulus of z is equals to r. So we are saying, sorry about that, let's just expand it. We are saying r, let's just continue, a small hitch. We are here, we are saying that r is equals to the modulus of z. Now here we have 10 into cos 120 degrees plus I sin 120 degrees. That gives us 10 into cos 120 degrees. When we're using the triangle, we will get negative a half plus I sin 120 degrees is the same as root 3 over 2. And now when we simplify, that gives us negative 5 plus I root 3, 5. But now we have a 5 somewhere because I 5 root 3. When we simplify, let's just write it here clearly. We will have minus 5 plus I 5 root 3. And now this one is from, we're given the angle and the modulus, asked to find z. In cases where you are given z in the form x plus iy, assuming you're given z is equals to x plus iy, and you're asked to write it in the polar form, you'll have to find r, and r is equals to the modulus, and then you'll have to find theta using tan inverse y over x, and then you write it in the form z is equals to r e I theta, which is quite relatively easy. The next area we're going to look at, we're going to go through, because this is an introductory part, is called the De Moivre's theorem. This theorem was named after De Moivre's theorem. We have De Moivre's theorem, named after the famous mathematician called De Moivre, and the theorem states that, so we have z. The theorem says that z is equals to z power n is equals to r power n. Let's just write it here. That was a technical hitch, sorry about that. The De Moivre's theorem states that z power n is equals to r power n into cos n theta plus I sin n theta, which means we have r power n into e, or let's just write it as one thing. We have r power n e I n theta. That's the De Moivre's theorem. And now, from the De Moivre's theorem, it means you can easily get the root of a complex number. We will handle it in our next video, but now let's just mention it. It means our nth root is z power n is equals to r power n into, we have r power n into cos, now let's just write it as 1. We will have into r cos theta plus I sin theta raised to power 1 over n. That means we will have r power 1 over n into cos theta plus 2 pi k over n plus I sin theta plus 2 pi k over n. And you know we are adding plus 2 pi k because we have 2 pi k possible angles. So we are adding it there, meaning we can get as many as we want, as many roots as we want. But now that one will be handled in a special video. And another thing we have is we can use how we can apply the polar form of a complex number. We can apply them in division and subdivision and multiplication. Now let's see applications of polar form. Applications of polar forms, and we are going to apply these applications in multiplication and division. We have z1 is equals to r1 into cos theta 1 plus I sin theta 1, and then z2 is equals to r2 into cos theta 2 plus I sin theta 2. And now if you are multiplying z1 and z2, it means we will have r1 r2 into cos of theta 1 plus theta 2 plus I sin theta 1 plus theta 2. and if it was for multiplication, we will have division z1 over z2 will be equal to r1 over r2 into cos theta 1 minus theta 2 plus I sine theta 1 minus sine theta 2. And now you need to take note that these applications of polar form are used when you're dividing complex numbers with a power which is above 1. We have a simple example here. We are going to solve the division part. We are given I1 plus I raised to power 6. It's dividing 1 minus I root 3 raised to power 4. As you see here, you cannot rationalize because first the power is quite different. Now our first step is to identify our R1. Our R1 is 1 plus I. We are going to write it in the form Z is equal to X plus IY, and then we apply the De Moivre's theorem. So we are going to find our R. Our R is 1 squared plus 1 squared, which is root 2. And then we're going to find theta. Theta is tan inverse 1 over 1, which gives us pi over 4. That's 45 degrees. And now our R1 will be root 2 into cos pi over 4 plus I sine pi over 4. But now remember, it's raised to power 6. We apply De Moivre's theorem. Now we have I1 plus I raised to power 6 is equal to root 2 into cos pi over 4 plus I sine pi over 4 raised to power 6. That gives us 8 into cos 6 pi over 4 plus I sine 6 pi over 4. And then we go to the next thing. You're going to have 1 minus I root 3. We're going to find our R. Our R is 1 squared plus negative root 3 squared. That is 1. We have 1 plus negative root 3 squared, that is 4. 1 plus 3, which is 4, and it gives us 2. And then our theta is tan inverse negative root 3 over 1, which gives us negative pi over 3. And now when we write it in the form of Z, we have Z is equal to R, which is 2 into cos minus pi over 3 plus I sine minus pi over 3. But now we have 1 minus root 3 raised to power 4. We are going to have 2 into cos minus pi over 3 plus I sine minus pi over 3. And now we are going to raise it to power 4. We apply the De Moivre's theorem like in the other case. 2 raised to power 4 gives us 16 into cos minus 4 pi over 3 plus I sine minus 4 pi over 3. Now we have Z1, we have Z2. So when you are getting Z1 over Z2, we have said we are putting R1 over R2 into cos theta 1 minus theta 2 plus I sine theta 1 minus theta 2. In our case, we have 8. This is our R1. We have our R2. We are going to divide 8 over 16 is a half into cos. This cos here, cos 6 over 4 is the same as cos 3 over 2. We are going to have cos 3 pi over 2 minus 4 over 3, so it becomes plus 4 pi over 3 plus I sine 3 pi over 2 minus it becomes plus 4 pi over 3. And this is our quotient, because we are dividing, will be a half cos. If you add, you get 17 pi over 6 plus I sine 17 over 6 pi. And that's how we apply the polar form in solving the quotient and product of complex numbers which have a power which is raised to a number which is more than 1. Thank you for joining us. Stay tuned for more on complex analysis. Bye.